to recap what we did last time, we were talking about doing multiple regressions with the mean data. That is, vectors taken, deviated from their means. So we get rid of the constant. So what I have here is y, as explained by a demeaned x1 and a demeaned x2. Now, there were three rules for finding those estimators. Now here is x2 and here's x1. In this case 2, I'm trying to make them, is that a right enough angle?
Sure.
Yeah, okay, so that's a right angle. So what we're going to do is follow our three manipulation of vector steps. The first manipulation is the orthogonal. Okay, the orthogonal rule. And in order to minimize the error here, the difference between y and that value of y I want predicted by my independent variables x1 and x2, I drop it straight down into the plane. Okay, that's the orthogonal rule. Then remember that the parallelogram rule was that, well, this vector here is going to be a sum of two vectors, portions of these two vectors here, and the portion of this one here, this is going to be parallel to that, and this is going to be parallel to that, okay, like so. And last time we talked about bias when we left out a variable. Now suppose in this case too I leave out x2, okay, only have x1. So instead of projecting on this plane, I'm just projecting on the line and ignoring the influence of x2. Now in the case where I have independent variables that are orthogonal to each other, that projection would be something like, in fact it'd be exactly like that. Is there any bias in this when I just regress y on x1 alone, ignoring x2? In the case, well, this is the estimator when both of them are considered. This is the case when just the one is considered in the analysis, but the other one is orthogonal to it, so it has no independent influence that's correlated with x1. So the bias, there is no bias. As long as my omitted variable, see if I project straight down orthogonally onto the vector here, I get the same answer as I do when I have both variables in the analysis. So we didn't consider that case last time. Let's go back to the correlated regressor case that we did talk about. And what I have here then is I have a case where there's a negative covariance where these are greater than 90 degrees. And that looks like the air was holding out on me. It's always holding out. There you go. There's x1 and there's x2 and there's a negative covariance between them. So they are related. And with those kinds of cases when I have correlation or covariance between the x's, I get in trouble. Okay, let's go through our three-step model here when we have negative covariance. So here in this case here, I'm going to follow my three rules. The first one is I take that out and tack it down so it doesn't disappear. So here's my y, my actual value of y up here. Little star means demeaned. So I want to predict it in terms of my independent variables. And in this case, the true independent variables in my classical measurement error problem are an x here, an x1, and an error here. This is the measurement error on the key independent variable that should have been included in my analysis, but I don't observe it. So if I had observed it, and I do observe my measured x, then what I would use, again, is the three steps. The first step is the orthogonal rule down into the x, so this is at right angle to the plane. Then the parallelogram rule, where I have a parallelogram. See, I have creating my parallelogram here. And if I had observed this other variable, this would be this part of the parallelogram, here. So does that look like that's parallelogram enough? Kind of. Okay. We should be a little further over. And the third is the proportion rule. And that is, what are my coefficients that I actually estimate? Well, they are, given this outcome, suppose I fully observed everything, this would be beta 1 hat. It would be the proportion of the first vector that I used in describing my outcome, and this turns out to be another beta, is a proportion of the error term I'd use in describing my data. It turns out in the classical error model they're the same. Okay, now what's the problem again? What's the problem is I don't observe the error, that it's omitted, and so when I do my 3 rules here, I get the true estimate here, but now suppose I don't have this error, I don't know what it is. There's a measurement error not known to the regression error. So when I regress y down onto the x ignoring that measurement error, what I get as a right angle here, right, that's the right angle here, is I get an actual estimated value that is less than the true value. And that's called attenuation bias. Last time, this is an example where beta 1 is positive, right? Because I'm taking a positive fraction of this x1 variable. A negative would flip it over and be over here. If beta 1 were negative, I would flip this axis over. I would flip this axis over to there, and I'd still have it biased towards 0. So whether the coefficient is positive or negative, when I have classical error, I have an omitted error problem in which the true beta 1 hat here is going to be biased towards 0. So how do we fix that? So remember, the other mechanical thing that we got from this regression as a review OLS regression was the r squared. Between the vector here, the predicted value of y in the plane, and the actual value of y, there's an angle here. The cosine squared of that angle is the r squared measure. So when the angle is 0, the cosine of a 0 angle is 1. The r squared is 1. I'm completely explaining without error my y in terms of x's when that's the case. On the other hand, what's the cosine of a 90-degree angle? It's 0. So when I'm 90 degrees here, I am completely unexplaining everything. So the r squared is 0. So r squared is between 0, which is kind of not good, and 1, which is kind of good, okay? So it's a measure of overall fit. It's the amount of variation in y explained by variation in the x's here, okay? Now what can we do about this in this measurement error problem? What we can do about it is get what's called an instrumental variable to help us out. Now we know that from our picture here, right here, let's go back and put our error in here. We know that the true coefficient that we should be getting is something like this. It's this fraction. That'd be maybe a third of the total distance. Our coefficient would be a third in this case, okay? If that were our sample. But we know that when we estimate it without knowledge of this error term, it's not going to be a third, it's going to be less than a third because of attenuation bias. An instrumental variable is another variable you drag in from the outside that has 2 properties. One, it's uncorrelated with the omitted variable, so it's at right angles, and 2, it's correlated with the x. And there's a 2-step procedure with instrumental variables. It's quite easy, really. So now, the first property, and both properties are very important, but this is essential that my red instrumental variable is independent of the omitted variable. It's uncorrelated with it. So what does that mean? Be right angles, right? So here, what do you think? You think you got one here that's about right? There's a right angle, okay? So what do you do when you have such an instrumental variable as this? It's a 2-step procedure. In the first step, what you do is you rotate this around, since you know you're going to run out of room. Here. Okay, in the first step, what you're going to do is you're going to regress your x onto the instrumental variable. Okay? So if I regress my x onto the instrumental variable, that means this is my y, and this is my independent variable, and I just use my covariance to variance formula. And if I did that, I would project it down on here, and I get this right, this sort of orthogonal projection here, right? So now this takes the place of my regression space in this example. So I'm regressing x onto the instrumental variable. And I get a predicted value of x. Okay? Second step then is I regress y onto my instrumental variable. Okay? So we're going to regress y down here onto our instrumental variable. And so again, this needs to be at right angles. Does that look right to you? If I've done this right, if I regress it down onto here, what I get will be this. Okay? I get the coefficient here from regressing y on the predicted value of x using my instrumental variable. Now, is this the right fraction of this? That is the length of this to that, my predicted value of x, given my instrumental variable, the same as the relationship between here and the overall length of this? How about this to that? Is that the same as this to that? And the answer is yes, because of something we call similar triangles. Right? Similar triangles, says two triangles have all the same angles, then these proportions will be the same in the two. And that's all there is to instrumental variable analysis, is just using our three properties on matrix and this fourth one of similar triangles, and we get the right estimated coefficient as long as we can find this instrumental variable that is independent of the errors, not uncorrelated with the errors, but correlated with the x's.